Okay, so the task for today is to finish up our discussion of two-way tables and to also talk a little bit about the projects and then also to do a little bit of review as well. So let's start with two-way tables. We don't need to worry about that other stuff for the moment. I do want to finish on a coherent note here. Now, we got pretty far on this material. Can anyone in the room, I know it's a little bit of a sparse audience here, or who's on Zoom, you are on mic if you want to speak up, tell us what the idea of a two-way table is. Like what sorts of things does it show us? And then how do we check for a relationship between two variables? So the idea is that we basically write down the individual functions, the probability mass functions, which are nothing scary. They're just a list of the percentages associated with values of a discrete or categorical variable. And we do it for both variables. And the idea is that when we do it in this way for this type of table, we can actually get a sense of two variables are related because we can look at the overall distributions here and here. These are known as the marginal distributions. And if they differ inside of the table, that is the conditional distributions differ, we know the variables are probably related. We're not going to deal with the problem of sample to population inference here. And if they appear to be unrelated, so the distributions in the margins more or less mirror those inside of the table, whichever way you calculate them, you probably don't have a relationship. So recall that we were picking up with this kind of interesting example here of the relationship between someone's race and their confidence in organized labor. And I was asking you all to think about kind of a tricky point here. So people in the room wanted to talk to someone near you. People on Zoom, can we do breakout groups? I think that's a thing. Let's see if I can pull up the controls here. Sorry, this is slightly awkward. Okay, people at home on Zoom, just think about this on your own. But think about it for a second. What appears to be the relationship between race and confidence in organized labor here? And also, which groups seem to be most favorable towards the cause of organized labor? So at home, please think about that. I might ask for someone on Zoom, just so I know I'm not talking to a dead audience, to dive in. But people in the room, if you would also try to talk to someone near you, let's think about it. So 2 questions. Is there a relationship? And secondly, which groups seem to be most favorable to organized labor? To make some new friends, try to do a little shouting. And people at home on Zoom, if you want to get in the chat too, that's also great. I'll read your response out loud. We've got about 20-ish people in here, so it's not, cause is not lost, maybe 15. Closer to 15.
Right, there's more like right.
So hearing lots of good comments. Could you share with us? That's kind of the answer I'm looking for exactly. Go for it. I'm going to use the clicker too, just so.
So it looks like white people have the most in every single category, but that's just for overwhelmingly the most sampled. And compared to the other 2 categories, there's a lot more white people, so of course,
Excellent. So the first thing to note here is that we've calculated column conditional probabilities, which means that we've found the percentages of each cell by then looking at the bottom of the column and dividing to get the percent. So here you can see whites in this marginal or overall distribution or unconditional distribution are a majority. They're about 71%. This is the GSS race variable. It's pretty crude, but they're about 71%. So that means that they're likely to be the majority of every group, unless they're really disproportionately unfavorable to some policy. But in fact, although it's tempting to say that whites have the highest degree of confidence in organized labor, what's the relevant comparison here? We want to look at the distribution of great deal of confidence to that of the marginal. And folks on Zoom, I do like kind of doing this over here on this slide. So I'm going to move, just imagine So if we look at this leftmost column here, note that even though whites are the majority, it's still tilted actually more in favor of other respondents and Black respondents, because Black respondents were only about 18% of respondents, other were only about 11%. But among those who have a great deal of confidence, they were 20 and 13% respectively, Black and other respondents. This means that they're disproportionately likely to favor the cause of organized labor, and whites are disproportionately unlikely. So it doesn't matter that whites are the majority, whites are already the majority. What we want to know is, are whites over or underrepresented among those who are more confident? Now, you might think this is a really bass-ackwards way of doing this, and it requires a little bit of careful thinking. And you would be right. So the reason I'm showing this is that it's to make a point. Even though this slide does work, it might be most meaningful to show, back here we did this last time, it might be most meaningful to show instead something where we condition on race. So when we conditioned on race and we found probabilities or percentages by taking each cell and dividing by the row, that more directly told us what the distribution of favorability towards organized labor was by someone's race. So for example, here we can immediately see that whites who had a great deal of confidence were only about 13% of white respondents, but among Black and other respondents, about 16 and 16.5% respectively had a great deal of confidence. And so that gives us a clearer picture of what's happening here. Any questions on that and on the general topic of inverting two-way tables? So both of those are allowed mathematically, but you might notice that one of them is much more intuitive. So why is one much more intuitive? Let me give a sense for why that is. This is all stuff I just said out loud. In general, we think that these fundamental social groups tend to be the causal variable. And so it a lot of times is just more intuitive to think conditional on your fundamental causal variable, such as your race or your gender. Your confidence in organized labor is a pretty core political view, but it's not as durable as your race. Your race is much less likely to change over the course of your lifetime, as would be your gender. Although again, even though people go through these gender transitions, it's still probably the case that that's going to be a less frequent source of variation than your views on a particular political subject, therefore condition on the more durable of the two things. Another really common kind of practical reason is that we also have an implicit baseline when we think about groups. So 50% of this group or more supports a policy is really easy to understand and interpret. It's much harder to interpret something like, well, whites are the majority overall, but they're a super majority of the people that favor this policy. Like, people that don't have much mathematical training tend to find that confusing, even though in theory it should make a lot of sense, right? So whites are already a majority, but they're 90% of, say, I don't know, individuals who practice a particular variance of Christianity or something like that. In theory, that shouldn't be too hard to understand. In practice, it's very often confusing for people. So it's much better to say, conditional on someone's race or gender or whatever the variable you believe to be causal, this is the distribution. We're going to do a little more practice because I know there is a lot going on here. And by the way, on tests and quizzes and that sort of thing on your projects, we will ask you to think about carefully, not just does the two-way table, does it make sense in some meaningful or some minimal sense? Like, does it have any meaning at all? Because no matter which way you do it, it has meaning. But did you do it in a way that makes sense for the question you're trying to pose? And here, presumably, we would think that race causes opinions on organized labor, or at least predicts it. And so that's why we want to calculate percentages that way. And that's all the stuff I said here. In general, if you are not sure how to interpret a two-way table, you must compare the distribution. So again, in this case, even just looking at whites, even though it's pretty easy to interpret what it means for 13% of whites, 65% of whites, and 22% of whites to think these things, we should still compare it to the other available options, Black and other, or just the marginal distribution, which basically is a weighted sum of the all three groups' positions, basically. So let's look at another example, since we've looked at that one quite a bit. We're going to do this by hand first. We've got political views here. This is also GSS data and firm preference. The GSS asks a really interesting question. What kind of firm, and for non-econ people, that's a business, would you like to work for? One owned by the state, one owned by the workers of that firm, or one owned by the GSS says something like private outside management that owns the firm, which is a giant mouthful. So I use the equivalent, which is probably just capitalist. So this is a really interesting question, and the results may surprise you. But I want you to first talk to someone near you in person here and then on Zoom. Think about it. Maybe you're with someone in the class, talk to them there. What way should you calculate percentages here? What way would make more sense? There might be multiple right answers, but I want you to justify it. So think, which variable do you believe to be causal? And then what should I do once I figured that out? Let's see a show of hands. Maybe we can do a quick Zoom poll. Is that possible? I think I can do that. Yeah, here we go. Okay. And I want to hear in the class too. So sorry, this thing. Anytime anyone jumps in the thing, by the way, it totally moves my cursor out. Apologies. Okay, so which way should we condition? Let's see, row or column. Guys, if you can avoid leaving and coming back, sorry, it just requires manual attention for me. That's probably a mistake I made. So sorry about that, but it does make it a little bit harder. Okay, so should we condition on rows or columns? We'll let people go ahead and answer here. Does someone in the class want to share with us which way they picked and why? I'm not sure how to access the poll. Launch. Sorry. Yep. I just needed to launch it. Okay. You should be able to see it. Yeah, go for it. Sorry. Sure.
What you believe kind of becomes a problem.
Yeah. Okay. Sure. So maybe this is just a more fundamental ideological position. This is a secondary one. So then what would you do once you've made that determination? Which way should you take the percentages? Like, let's pick a concrete example. Let's say we want to figure out what to do with this cell here at 31. Should we divide it by 119 to share people who prefer state-owned enterprise, or should we divide it by 380, the number of liberals? Okay, great, totally fine. Good start. I think that's a reasonable kind of social theoretical claim. What about mathematically? Yeah, go for it. Great, so taking it across the rows, go ahead. Yeah. Right. Sure. Excellent. So what we would want to do then is, if we think the political views are the causal variable, it's a little bit easier to interpret then if we figure out of liberals, out of moderates, out of conservatives, what share of people prefer each of these types of governance. Did anyone have an alternative sociological theory where you start the other way? Yeah, go for it.
How they want to work.
Mhm.
And that can apply to the certain party.
Sure. 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 Yeah, this would be another way of thinking about politics. It could be right or wrong empirically. It might also be a way that some people would advocate that you should think about politics. So starting with, what do you think democracy looks like or shouldn't look like possibly in your daily life? And maybe then that forms your broader political views. That's a really interesting question in political sociology. Actually, David, the TA who's with us today, and I got started by teaching for someone at Eric Olin Wright who had a great interest in exactly this type of question. You could arguably go either way. So let's look at it right here, though. So I want to ask this question before I say too much more. Which way have I calculated percentages here? Can you tell? And what story does this tell you? Okay, don't think anything. Yeah, we got the poll set up. Cool. Okay, I'm going to end the poll. By the way, most people at home said row, which is correct, about 75-25 rounding. Nice job. Okay, so which way did I calculate percentages here? And how can you tell? Connor again? Yep. Excellent. So they add up to 100 here. We can also usually eyeball some things too. So 70 over 380 should be pretty easy to eyeball. But the idea is when you calculate it, say for rows, the point is that you should be able to directly compare across rows. So these numbers should not only all add up to 100, but unless you have wildly divergent distributions, the numbers should be somewhere in the ballpark of each other. And they are, right? So we see that most people selected employee-owned, some people selected capitalist-owned, some people selected state-owned. Very interestingly, liberals selected state-owned with the least kind of prominence there, which is kind of an interesting finding. So they were more likely than moderates, in fact, to say that they would prefer to work for a capitalist-owned firm, although it's not a giant difference. We'll see later on that it's hard to draw deep conclusions from these things because these are small sample sizes and subsample sizes, but avoiding that problem for now, it's kind of an interesting finding. Cool. So then what if we look at it this way? We already know the answer, but we've calculated the percentages here column-wise. I want to see if people can make sense of this. So can you convince yourself that when I just flipped the way we calculated the percentages here, we didn't change anything fundamental? Take a second, talk to someone near you, see if you can explain how this also shows the same story. And let's maybe pick one conclusion from the last slide, just so we have one in mind. So note the surprising finding that actually, if you look at it here, liberals were the least likely to say that they would like to work for a state-owned enterprise. So can you convince yourself that that's true using this column calculated table? Try that on your own really quick, see what would be the relevant comparisons. And again, people in Zoom, I would love if anyone wants to jump in and let me know. Happy to read it to the class. Seen lots of good stuff here. So what share of respondents overall identified themselves as liberals? Go for it.
28%.
Oh, sorry, you both answered. Yeah, 28%. Great. You want to answer the next question or do you want to explain? Seems like you got it.
I don't know, yeah, I guess 28%.
Sure. 28 or 29%. Yeah. Then if we look at conditional on you preferring a state-owned enterprise, what was your probability of being a liberal? It was 26%, lower than it was overall. So that indicates that there is this relationship that is surprising. It's just a little bit easier to see on that previous table, right? Here we see directly, liberals are actually, again, I know it's a little bit weird, but politics are weird in the US, and a lot of people don't think that politics and this sort of question have anything to do with each other, which is maybe surprising, but it's true. But here it's a little bit harder. What we need to do is think about what was the overall distribution of political views and then the distribution of political views within certain categories. But then once we do that, we see that there is this relationship that we saw on the last slide. I wanted to note one more thing too. All else equal, putting something on the columns and the rows before you calculate percentages doesn't change anything. Sometimes people get a little bit thrown off by this. If you do this in Stata before you calculate percentages, you can just decide which one looks better. A practical tip in Stata is you want your tables, sorry, I guess they didn't use chalk the last hour. Maybe they weren't here. You don't want your tables to spill over really wildly. So if you have a table in Stata that's got very many values, you want it to look something like this. So folks at home, I'm drawing like an example table on the board where we've got n rows here. Maybe it's something like 13 or 14. Maybe you're working with the GSS religion variable, and you've just got a few items on the columns. That's probably better aesthetically. Why don't we actually just look at an example? So we'll pull up the GSS in Stata. Okay, so if we tabulate something like religion, and let's just say we'll do a simple one, we'll do sex, which is how they refer to biological sex here. This doesn't look too bad, right? This is relatively easy to look at. What would happen if we reverse the two? Now this spills over. So this is a pretty common beginner mistake. There is no mathematical difference. We don't really have to worry about whether it's going to be right or wrong, but notice that this is very hard to read. So you want to think about putting the correct variable on the rows and the correct one on the columns. Stata syntax is to put the row variable first. Stata syntax for which variable goes first when it matters is not always consistent. So you just need to remember it for particular commands or test it out, right? So you can make mistakes. I honestly didn't remember off the top of my head, and I just knew that if it looked bad, I would swap it, and if it looked good, I would swap it. So that's just how coding works. Now let's actually play around with this a little bit. You'll see this in lab 2. How do you think we should calculate, say, percentages for this first table here? I'm going to pop it up again. So is there a way that would make more sense if we were interested in the difference between, say, religious preferences by sex? Is there one that would be better here? One that might be slightly more intuitive? And people's gender identities change often. Well, relatively often, more than you might expect. But sex and gender, which are different, but they can both change in a certain sense, are really durable, right? Religion tends to change over the course of people's lives, especially in societies that are growing more and more secular. So I think we should pick here columns. So let's do that. So how would we do that? We would say comma col. This is still kind of a lot to look at, but what it allows us to do is say, conditional on someone being male or female, what are their preferences? And we can see here that there's some minor distinctions, which is kind of interesting. In particular, male respondents are vastly more likely to say they had no religion, which is a fact. Okay, cool. So that's all I have about two-way tables. Let's not quite go to a break. I think we'll do that after the review. Let's go back to the new material, and I want to offer a few announcements. So you have the quiz coming up. We're going to do some review right away. The proposal for the first data analysis project, with which you can use GSS data or CPS, current population survey data, is due next Friday. The proposal is published. Here's what you need to tell us. And by the way, I know sometimes people evidently haven't submitted a project proposal before, so don't freak out. This is not the project, it's a proposal. You're just going to tell us what you want to do. You want to say what variables you'll use, what kind they are, so qualitative, quantitative, and within that, what are their subtypes? So nominal, ordinal, ratio, interval. What kind of strategy follows, what you expect to find, what you need help with, and that's pretty much it. Now, we have only discussed two main types of analysis so far: two-way tables for qualitative, qualitative, and regression and correlation for quantitative, quantitative. If you have a qualitative predictor and a quantitative outcome, it's very easy. You want to compare conditional means. A conditional mean is just the mean for a group. So conditional on, just like we were talking about before, you being a member of this group or that group, which is the same thing as you having a value on this qualitative variable. The one final possibility, and I'll show you, by the way, that this is in the, let me show you a guide to this that's in the material. The one final possibility is you might have a quantitative predictor and a qualitative outcome. Those are really tricky, and I recommend that you not tackle those unless you feel really comfortable with the material. It's hard to use linear regression on that. You can use a form of nonlinear regression known as logit. I have a tutorial on logit on my YouTube, but I really don't think you should try that unless all of this is feeling dead simple and you're just bored to tears with what I'm saying. If that's true, give it a go, but that may or may not be true for people. So let's look at the coded description here. And if you come down to the project instructions, to see what I just said aloud about the types of project, note that you can come down here and look at this 2x2 matrix that gives you a sense for what types of techniques you want to use. So we haven't talked about all of these yet. We've talked about two forms. We've got one left to cover, and then the other one I'm recommending that you try to avoid. It's surprisingly common. Lots of people want to know, for instance, does your years of education predict whether you're married? That's a qualitative outcome, quantitative predictor. It's mathematically, intrinsically kind of complicated. So just rethink it if you do come to that conclusion. But you've got these other three alternatives here. So quant, quant, we've gone over at some length, and qual, qual, we've now gone over at some length as well. So yeah, that should be enough to get you started. Here's the qual, qual. Okay, so questions on the data analysis project proposal from anyone? You do have other data sets you want to use, you're welcome to, but you do need to check them with us. The GSS, as messy as it is exceptionally clean. If you find other data, if you find a cool data set out there on the internet, odds are when you actually open it and start using it, it's going to be a little bit disappointing because it'll probably be very messy and unpleasant to deal with at first. That's just how data are. Yeah, that's pretty much it. If you did happen to look at this, I said I would make some changes. Really, all I did, David alerted me to the fact that there were some ambiguities in the wording, so I cleaned that up. Otherwise, the only things that actually changed are just about the submission. We want a PDF, and we do want your do file. That's to respectively deal with some wrangling problems with Word. Word is really terrible, so please submit a PDF. And the do file is just because we're putting more emphasis on Stata this semester, trying to give people a better reward structure for learning it, because it is challenging. So we want to see your hard work and reward you for that. Finally, homework 3 stuff. Basically, again, submit a do file. I did want to clear up some grading snafus that I introduced last time. So there's a really clear rubric for the do files. They're worth 4 points. It's not a big part of the homework, but it's 3 points. And you really have to use Stata to do the homework well. So you should be doing this anyways. Here's how the 4 points are allocated. Submit anything that's a do file. That's a point. Use my file naming convention, which will save you a lot of heartache. Tons of people uploaded the wrong file. I know, it's just natural. It's part of being new to doing, computer stuff consistently, but like 7 or 8 people put up a data file or put up a lab file instead of the homework. So please do follow my file naming convention. Make sure you establish a working directory. That's a key part of learning how to manage data at this level, even if you can later dispense with it, as David might argue. And then give a reasonable effort at every question. So make sure you number these and then just show us, where you're trying each question. A couple of points, and these are fine points that I wouldn't expect anyone to know and that come up every semester. You don't need to paste output into your do file. Your do file basically produces the output, and your TAs and I can read code, so to speak. So we can tell from your code what's going to happen. We've been using Stata for a long time. You don't need to show us necessarily. You can always submit log files too if you want. That does do that, but we really don't need that at this level. You're using super common commands that we know. So you can just submit your do file. You don't have to go to the trouble to paste the output in. Asterisks are required to put it in comments at this level. We can use different means of making comments, but make sure you're not just writing comments as code, right? So let me show you what that means. Don't do this, basically. This does not work because this is not Stata code. But if I do this, well, I should not do a performative contradiction. This does work. Yeah, this does work. This is not recognized as code. Stata knows to just reprint it. So that's something to think about. Your do file must also run all in one go. I actually don't have an example off the top of my head. Basically, all it needs to do to run in one go is you need to change the directory to a place where the data exists, load the data, clear the data, run the commands. So we've been practicing that in labs. You can see a lot of examples that I've uploaded to various places, but yeah, make sure it runs all in one go as well. That's more for you than it is for us. Finally, one last thing. So we're running a little low on time. We won't cover experiments in more than very brief detail. They're super interesting, but the reason that we spend so much time on inference in this class is that we don't do experiments. So this is kind of just bonus material. Okay, with all of that said, let's talk about the quiz. So this is what the quiz will look like. I decided to be a little more indulgent this semester and show the structure. So you can see we'll have some questions about distribution, the area under the curve properties, numeric questions, some caveats, so some like big things to be aware of. We've talked about caveats every lecture, basically. We will do a little bit of Stata. The Stata stuff is not going to be challenging. And then I do love asking some bonus questions. So you've got some conceptual or very, very basic proofs that you can answer for bonus questions. The calculation is not going to be super tedious, so we're not going to do correlation coefficient by hand. You may need to do the regression slope, but well, sorry, that's for the next quiz too. So also no regression on this. For the next quiz, you may need to do regression by hand, but that's super simple. So we're not going to do anything that involves lots of summations for this quiz. It's tilted more towards graph and concrete questions. So even though I like to talk a lot about conceptual stuff in lecture, that's really more for your understanding. The conceptual stuff is, things that you really just need to be a common sense practitioner. So knowing, for instance, that R can't be 100, or that R of 0.1 doesn't mean, R of 0.9 doesn't mean very small correlation. It means very large correlation. That's a conceptual question, but it's also just kind of a common sense question. If you're going to be a practitioner. It is open internet, open note, and open Stata. You're more than welcome to try the Stata commands on the Stata questions. So don't be afraid to use whatever resources you have. Please don't use ChatGPT or any other like super fancy AI, and try not to use, well, don't use other human assistants. This is an outline. Do people have any questions here or in the chat? About the quiz? Yeah. Yeah.
Hours was to save on a Mac.
Save on a Mac. I think I understand, but maybe not. Can you say more?
Like for saving a do file.
Yes.
Mac,
Yes.
on like the location, like I've
Yeah.
done it multiple times.
Say more about doesn't work. So you mean, this is probably useful for everyone because this is something that I could imagine coming up in a lot of ways. So when you say, like, let's say we have this example do file. So we want to save this. So I'll click Command S. I know lots of people have Macs, not everyone. Okay, so then next step, I would probably move it to my do file folder here and title it something like that. And then is this part, so like at this point, it's not working basically.
Oh no, I just like when I write it in it, but now I see where it's.
Okay, cool. Yeah, so if anyone hadn't seen that before or was having trouble with that, hope that was helpful. Thanks, good question. Okay, so let's start on Top Hat to reward attendance. This should work for everyone at home, I think, because I have to turn on geolocation actively on Top Hat. Whoops, this is also the wrong one. So I think that means the default is not geolocated. So let's look at the first question. This is in the review. I'm just turning it into a Top Hat question as well. Let's do this. Folks, can like 2 people in the comments in Zoom let me know if you're able to do this, and I'll give a full 2 minutes here. So this is men and women, men in red, women in green. This is stress by sex. Yes, okay, yeah. Cool. I think we're good. Yeah, thanks. No need to weigh in any further unless you have trouble. I'm glad that this works. This is great. Okay, so this is kind of a fancy looking histogram. It's a little bit translucent. You can see 2 overlaid, but otherwise nothing changes. So who, generally speaking, has higher reported levels of stress? What direction is the skew? And then what does that mean about the mean median relationship? I'm sorry that we can't see the entire thing here, but again, men, red, women, green. Those are my 2 favorite colors. I have no preference, so I just assign them at random. This is more data from the Midas biomarker project, midlife US. Basically, they do a lot of tests to see, does stress and stuff show up in your vital statistics? Gathered by some people at UW, some people at Penn. It's very interesting data. Okay, so yeah, 30 seconds. Again, do throw something in just to get credit. I know there's a lot going on here. This would be pretty typical for the difficulty level of the quiz on this section. Wouldn't say it's harder or easier. Okay, 10 seconds. I gave 2 minutes on this, so I won't extend it. So please do get something in. Okay, so let's see how people did. Responses. So women had higher levels of stress. Great. And if we look here, we can see that that's evident in the fact that the green bars simply extend out further. It's a little bit offhanded, but you can see generally men have higher frequencies, or in this case, technically speaking, densities or simulated densities at the lower end, women at the higher end. Great. Okay, I think I can do the next one? Yeah. Let's see, how do we do multiple answers?
On the top one, it says like link to.
Ah, I got it. Thanks. Yeah, you guys are smarter than I am. Okay, so it is right skewed or positive, as someone put. Yeah, these are both right skewed. Why? Anyone here in class help us out? Yeah, go for it. Thanks.
They have a kind of tail.
Yeah. They have a tail going off to the right, and it appears that this scale is likely unbounded, or at a minimum, the highest scores reached are going to be higher than anyone would ever actually feel. But there's a lower bound it appears from this kind of data, you typically can't score a negative on this data. So it's also known as less censored data that typically produces a skew. Much like with income, right? You might think of income as measuring some kind of underlying propensity that could maybe be unbounded, negative and positive, but unless you have a really weird debt situation, you can't have negative income. So since you can have positive infinity income or something close to it, that means that that underlying propensity is expressed only in one direction. You get a right skew. That's kind of a high-minded explanation, and also some things are just right and left skewed. Okay, and then finally, that means generally speaking, yes, and this follows from the last one, that the mean is generally speaking greater than the median. Again, the balance point intuition is a very nice way to think about it. If we think about the balance points here, they're not going to be where half the data are to the left, half the data are to the right. They're going to be a little bit further. If you imagine this being a weight that's balancing on a lever, because we've got these higher end observations. Okay, let's do one more top hat question. So I'll bump this up to 130. I think everyone's probably got time here. This is more MIDAS biomarker data. So perceived stress across values of one qualitative variable. Do you have all your teeth or not? What we're looking for here is the cut points of the data are larger for people who blank all their teeth, do or do not. And when I say cut points, I mean like compare 25th percentile to 25th percentile, et cetera. And both distributions have what kind of a slight skew? Okay, take 10 seconds. Okay, great. So let's see how people did. Okay, so do not have all their teeth. Okay. And then if we look at the second blank, both of them have a right skew. Yeah, let's pull up the graph one more time. So again, the cut points are larger for people who do not have all their teeth. If we come down here, those who had red were missing at least one tooth. I'm sorry that I did this out of order. And you can see that that's very slightly true. Principally, and this is maybe of more interest, the median, the 75th percentile of the stress score is higher. The bottom end is almost identical, but these two are more importantly a little bit higher. And both of them have a right skew because we can see, again, if we imagine a histogram of these data, this would be also the right end of the histogram. We've got some observations here that would be represented by far out to the right, but very small height, indicating low frequency values. Okay, cool. So let's do a little bit more review. So that's some material about distributions. And that appears here with detailed commentary on these two slides. So we already did that. I'm pulling some more physical data. So the percentage fat of people's heads is actually very close to normally distributed. I found this out by accident a couple semesters ago. We've got a mean here of 24.12 and a standard deviation of 0.63. It is just an intrinsically silly example. What would you guess the median to be here? Note that these are very normally distributed, like the closest to normal we've seen so far. Yeah, go for it. Yeah, 24.12 probably, if we had to guess. Great work. Great work. Okay, so now a tougher question. These are not quite normal, but they're very, very close. What share of people have 23 to 25% fat on their heads? And this forward slash in a lot of programming contexts means 23 to 25 inclusive, where 23-25 would be confusing. So what percent of people have 23 to 25% fat on their heads inclusive? We've got a question in the chat. Oh, maybe this is a, okay. All right, sorry about that. That's a direct one. Yeah, I'll fix that. Okay, So this is a Z-score question. We're going to need to do a little bit of calculation here. So I'd bust out that table A or your Z table. Let's calculate some Z-scores. So by the way, if you're unsure of where to start, a good first step is to draw a picture and shade the relevant area, and then find the associated Z-scores. So we have 23 and 25 here. And I've marked here on the slides, this is not exact, it's pretty close. But you want to find those these here. It's not exact because this is not a really continuous distribution. So I made a judgment call about whether to include or not include, but for a truly continuous distribution, remember, it does not make any difference. So let's try to find one of the Z-scores. Can someone walk me through their calculations for, say, the Z-score for 23? How do we turn that into a score drawn from the standard normal distribution? So in case you're worried, the answer is right here. So we do it like this. We do 23 minus the mean, just 24.12. And we're going to divide out by the standard deviation, which here happens to be 0.63. And that happens to be our Z-score for, let's just say, 23%. And I can't do that in my head, so we get a score of negative 1.78. And then our next step is to go to table A or a Z table. You can also do this in Stata, and I have shown that in Stata, but let's do it with the Z table. And even if you don't have one handy, you can just Google Z table. This is a standard name for this thing. Probably this first result will be fine. And if we come down here, we can see negative 1.7. Then we're going to go all the way over to 8. So we'll be very careful, but we get right here. We get 0.0375. What does that number tell us? If we're going to, like, let's say, shade a normal curve. What does that number tell us there? Okay, go for it. Very good. So we get this here. And I haven't drawn this to scale, but that represents about 3 or 4%. Very good. Let's close this here. Do a little cleanup while we're at it. Okay. Great. So then our next step would be to do the same thing, but for the upper end. And I won't walk through that in too much detail, but you can see we would just swap out 23 for 25 and get 1.4. And we could do the same thing in the Z table. So 1.40, we come back here, we scroll down, we see 1.4, and then fortunately we're right at 0, so 0.9192. And then we come back here and we think about, how do I want to use those two numbers? So this right here for 1.4, we'll put it right about here. So let's write out the areas here in a kind of coherent way. So we have the probability that a z, any old z-score from a normal will be less than negative 1.78 or less than or equal to negative 1.78. It doesn't make a difference, is 3.75%. And that same probability, but for a z-score of 1.4 is equal to what? 0.9192% or 91.2% or 0.9192. And that is represented here. You'll have to forgive me, I can't draw in colors here. I'm going to crosshatch. So this is that first probability. I'll just denote it P1. The second probability here, P2, is displayed graphically like so. But what I want is actually this area in the middle here. So what should I do with P2 and P1? How should I use these two probabilities that I found? Yeah, go for it. Excellent. Subtract P1 from P2 to get the final answer. So we're going to take away 375 from 9192. Great job. So the answer is, you can intuitively guess somewhere going to be around 0.8817. That's a probability of 88%. Great job. Yeah, thanks, Brian. That's a great answer in the chat too. Thanks. Excellent. Okay, really glad to see where everyone's at with this. Not bad at all. So that's the z-score problem solved. And for folks at home, the stuff I wrote on the board with z-scores in the probabilities is just the standard way of doing it. Just writing out what exactly it was that we found. So what does that z-score actually mean? It's a probability that any old z-score represented by a big Z is less than or equal to that particular one. And again, less than or equal to and less than, there is no distinction between those two things with a continuous distribution. I know that's weird, that's just math. Okay, so this is one way to think about what we did. We found the area under the curve of basically the standard normal. And here I drew our same curve, but I just made it standardized. And this looks pretty similar to that standard normal. So we basically converted these 2 points here, 23 and 25, to points on the standard normal, and then found the area under the curve between those 2 points on a standard normal. That's what that z-score business is about. And note that we could find the values of the x-axis enclosing the area under the curve here. So if we had this picture, negative 1.78 and 1.4, we could go back to this here by knowing the standard deviation and the mean. But there's one more way to think about this too that I think is pretty helpful. Oh, by the way, you don't have to do this in Stata. Remember that we have this tool. People tend to forget about it. But note this online stat book is an excellent resource. So we could have also solved that like this, 24.12, standard deviation of what was it, 0.63, I think. And then we want between, in this case, 23 and 25, and that gives the same answer. So it's way faster. Now you have to know what you're doing, right? I can do that really quickly because I know exactly what I'm doing. But if you do know what you're doing, it's fast. So that's the online stat book. It's linked several times throughout the notes. It's here as well. But I wanted to show one more way of thinking about this. We can also think about what is that stuff in table A? What is all that crap? Well, it's not values exactly from this, or if it's values exactly from this, what we would say is it's values for the area under the curve to the left of that point, which is a little bit counterintuitive. Maybe more intuitive in some ways is to think about it as this cumulative distribution function, because literally, if you look at what does table A say, it's values from the cumulative distribution function. So this is very literally where they come from. So we can see here that we found the point associated with 23. 23 is an input to the function. 0.375 is an output of the function, or 0.0375. And then 25 is an input to the function. And then 0.9192 is an output of the function. And then we just take the difference between the two. And that's more literally what we did using table A. We just looked at the x value for a function, and we found the y value, and we found the difference between 2 points. So I think this is also kind of a helpful way to think about it. And hint, there may be some distribution question on the exam that could be very much like that and a little bit challenging. So I wanted to show an example here. The exam won't be entirely reviewed. There might be a couple of little challenge questions. Here's one that I thought might be kind of interesting. So the book also discusses some other examples of probability density functions, not just normal. And they actually asked you at some length, although I didn't mention it in that lecture, to think about what a uniform distribution would look like. So knowing that this is the distribution of your date of birth for the United States in 2019. Again, this is 2019 data because COVID messed everything up. If this is the cumulative distribution for a different variable that has a different distribution, what do you think that probability density function looks like for this kind of cumulative distribution function, where it's extremely linear? Every time you go over one day of the year, your additional probability changes by the same amount. See if you can think about what that curve would look like. I'll give you a hint. It does not look like this Bell or Gaussian curve. What would that curve look like for this cumulative distribution function where I'm telling you they are uniformly distributed? If you have a math background, you'll immediately know the answer, but I presume you all don't know what the uniform distribution necessarily looks like. You can probably guess. Maybe talk to someone near you briefly, and folks at home, think if you can decide what the uniform probability density function would look like. Anyone got any guesses? Parabolic was close, on the right track.
Oh, I was gonna say that straight.
Okay, I might have been being really nice. Yeah, parabolic's a little bit off, actually. Yeah, straight across, very good. Yeah, parabolic's a good guess. So, yep, uniform distribution just looks like this. And one way to think about it is if that density is the speed of probability or the rate of change of probability, that rate of change is exactly constant. It's a perfect linear function, basically. So this thing is just going to be flat. Another way to think about it is if you just pick any random subset here to here, or here to here, or here to here, once you divide out by the different widths, the probability is going to be the same. So that is a uniform distribution. That's just one example of the many types of distributions that are out there. Again, this would be a difficult question on the exam, hint, hint, but understanding the relationship between those two things, and you can credit your TAs for pushing me to ask more about other distributions. But yeah, we're not going to ask anything too wild, and very, very nice. A lot of times you can infer what they would look like. Great job. These are roughly real data, by the way. You can't get real birth dates, but you can get information on months, and the distribution of births across months is extremely uniform. So people are not more fecund or less at any particular time of year. All right. Let's do something more bread and butter. Correlation. This is the last topic really covered on the exam. So let's ask a really simple question. Again, some physiological data because they're nice to work with mathematically. We see here the relationship between two closely related things, your right leg and your right arm. I did that backwards. The lean mass there. In other words, how much basically muscle do you have there, right? How much non-fat? What do you think the correlation is here? You just had to pick a number. Okay, someone in the chat has an answer. Let's see. Almost 1.9 people in the room. Feeling good about those answers? Yep, great. 0.9 and close to 1 would be great answers here. What about the relationship? So we've seen a lot of physiological data that seem pretty linear, maybe with a somewhat nonlinear component. I think that looks like it pretty much fits here. There's a bit of an odd shearing in this case, so some weirdly missing data there. And the spread gets a little bit more pronounced, but this appears to be a pretty linear relationship. Indeed, there has to be a very strong linear component for the correlation to be that large, even if you can have a correlation very near to 1 and still have some perceptible nonlinear pattern. Okay, so that's that. Any influential points worth examining? I know I gave the answer to the last couple of questions, but let's hear from the crowd on this. So any people we want to maybe take a second look at? Yeah. Yeah, these two people look like they may, in the first case, this person is right on the line, right? She or he is actually really strongly increasing the strength of the correlation. Not that much because the N is large, but we probably should still look at them. And this person here, if we get a correlation value that seems surprisingly small despite the obvious visual pattern, we may want to say, what's going on with this person who's just absolutely shredded below the waist, but then not so much above, above the torso there. So these are the two influential points that we do want to look at. And yeah, it's really bizarre, I think. It could be an amputee. Yes, that's a great point. Yeah, so use your substantial sociological knowledge, which is something I don't always have very much of. This person there might be a totally reasonable explanation. You would want to look at the code book. You can also, in a real data analysis project, get that person's ID number and just look at their file, which is easy to do in Stata. If you see this on the exam, it will be extremely easy to figure out. You won't have to hunt and peck and see. We might just say something like 2 subjects are marked, 1 and 2. Which one should be examined more closely? And it would be something like a person from right here and a person from right here. It won't be hard. Okay, so a little bit more about correlation. Ignore the regression component. This is a slide from last year's lecture on regression that I opted to omit. So I wanted to ask about this here, though. So what strength and form of the relationship on the left do you see? And then what about the one on the right? So this will be our last review question. How do these things relate? Someone's in the chat. Let's see. Strongly positively linear and strongly curvilinear. Very good. Yep. So this is an example. We didn't talk a ton about this, but one of the uses of logs, which are really useful at higher levels, is when we see these very nice parabolic relationships right here. So one between weight and standing height, where you can draw this, basically just y equals x squared with a little bit of fiddling. That usually indicates that there's a very nice linear relationship between the log of one and the linear component of the other. But yeah, in the original form here, this would be a classic example of a case where we can see an obvious relationship. And that relationship is so obvious that if we transform one of the variables, we can make it linear. You don't have to know anything about that for the exam. It's just a kind of fun example. But here, the main takeaway, R is going to be small here because it's not actually linear. So you can see a clear pattern, but you have to know the meaning of the tools we use. Don't be shocked if the R here is actually quite small. It's actually going to be fairly large because there's still an obvious, it's a remarkably exact relationship, but it's not a linear relationship. So again, don't mean to freak anyone out too much. You don't need to know anything about logs. Just saying this is a good example of how this looks like a strong relationship, but what's a strong relationship? It's between the log of that thing and the original. You don't have to know how to take logs. I'm just saying there's a difference between strong curvilinear relationship and a strong linear relationship. This one correlation addresses well. This one correlation addresses poorly. So those are the things I would like for you to be concerned about. Okay, I think this quiz is going to go super well. People tend to do very, very well on it. I did want to talk briefly about sampling. I know we don't have a ton of time, but that way we can zip past most of it next time. Again, we won't discuss experiments beyond one slide. Do you have questions about the exam? That's not absolutely everything. I think that's a fair guide, though. We didn't talk a lot about standard deviation and variance. You should know what those things represent. What's a good example? So for instance, you don't have to have the formula exactly memorized, but you should know enough about the formula to know that the standard deviation can be negative, cannot be negative. So it cannot ever be negative because we square all the points. So you need to know enough about it to know that. And again, that's like a property we like, right? Can spread ever be negative? Would you ever look at a set of data or, even if let's say you're going into a preschool or something and all the kids are basically the same height, right? Within, as far as you can tell, would you ever say that the spread is negative or just that there isn't really much spread, right? You'd say there's not much spread. So standard deviation also tracks our intuition there. Yeah, and then this material, I forgot that I put this slide in here actually, but that's pretty much what I just said out loud. So sorry about that. I forgot that I had a slide on it. Again, you don't need to know all these formulae. You just need to know roughly conceptually what's going on. So as I mentioned just out loud, this gives you a sense that standard deviation and variance can never be negative because there is a square in there. But otherwise, or maybe another kind of conceptual question that knowing the formula would help on, a question I've asked before in class. Can the correlation be sensitive to outliers? The answer is yes, because the correlation formula takes the deviations of people from the mean. So if someone has a very high deviation, they're an outlier, they can play a big role in the analysis. Otherwise, yeah, the the regression stuff won't appear on the exam. So all of this down here, you don't need to worry about. Let's talk a little bit about sampling. So the key problem of statistics, and one we have not yet addressed, even though I mentioned it a few times today, is we want information on the population. Can anyone remind us what the population means in statistics? Does it mean everybody in this state or everybody in the US? Like the actual population? No, it means the whole set of people or the things you care about. It doesn't have to be people. So our goal is to do inference about that population, but we only have the sample, which poses a conceptual problem. And that's what the whole second part of the course is about. We're going to keep using all the stuff we learned. We're actually not going to learn any really new statistics, believe it or not. So regression is the hardest bit. And that's where the course ends, is with regression again. But we're going to learn how to do inference on those things, which is a whole other concept. So we're not going to focus today so much on the problem of inference. We're just going to talk briefly about the method. And the method is really cool. We talked about this just a moment ago. These are all things we said out loud. I want to do a quick bit of like housekeeping here. So we'll need to consistently keep the sample and the population separate. And in general, almost always when we have Greek letters, those refer to parameters, and those are, to define it one more time, facts about the population that we care about that we don't directly observe. Literally, parameter means para, as in paramilitary, or I don't know, what's another example? Paramilitary basically means, not an official or not a true military. So parameter means something that is not actually measured or not truly measured. It's something we wish we could measure. And then the stuff we can actually measure in the sample we call statistics. And statistics usually have Roman letters. So the familiar letters that we use, those are Roman letters. And we use numbers to describe both. You don't need to know the entire Greek alphabet, but some letters that you'll often see: alpha, beta, we've seen beta already, mu down here. We'll see lambda sometimes. We've seen theta before. We'll sometimes see rho as well. That's the population correlation coefficient. We'll see pi on occasion. We've seen sigma a lot. Those are really the only ones that we need to know too much about. But you may want to, make sure you feel comfortable with those things. I know it can be a little bit intimidating and weird. Again, for people that have experience with Greek life, this is going to seem very basic. For people that don't, this is going to seem like, I wish I never knew this stuff, but they're just variants. There we go. Yeah, also that. Yeah, I didn't even think about that. Yeah, many of these, Omicron, if you ever wonder what that is, it just is like a no. All right, so this is a funny way to talk about sampling, and sorry that we don't have time for a break this time, but the best way to understand how to do sampling well is to think about how to do it poorly, because it's really easy to do it badly. So what are the two easiest ways to do it badly? A convenience sample, basically just asking whoever you see, right? You've probably done a sample like this. Has anyone ever done a sample like that for like a high school stats course or for 357? Not to talk smack on 357, which I also teach. Yep. Sometimes it's just all you can do, but you basically go and say, who's on the bus? Okay, you're in my experiment now. Sorry, don't care ethically. This is just your fate. And that's not a great way to ask people questions. The other one would be a self-selected sample. The book calls these voluntary response samples, but I don't really like that terminology because all samples are really voluntary. What we're concerned more about here is people getting into the sample. Can anyone, yeah, snowball sampling would be adjacent to convenience sampling. Now, yeah, so Trishan's asking that question too, and Trishan is a grad student and probably knows quite a bit more about call methods than I do. It's not always wrong to do these things, by the way. We're just saying what works or doesn't work for certain mathematical procedures. Yeah, great question. Yeah, so again, there's a whole lot of reason to use those things sometimes. I just don't have time to address them here, but it's not always wrong. Okay, so can anyone think of an example of what this abstract concept means here? Self-selected sample. Have you ever taken a poll where you felt like, I'm probably the only one answering this, or like I'm answering this because I really feel jazzed about this issue? Anyone ever taken a Twitter poll? No? Has anyone seen a Twitter poll? Okay, so who do you think answers those things, right? It's people that care about the poster and care a lot about the issue. Are those things you should ever take on faith? Absolutely not. No, Twitter polls mean nothing. And they're a classic example of a self-selected sample. Or if you're on a news site, this is kind of a boomer thing. I'm sure no one here has ever actually done this. Maybe your grandparents have. But if you're on a news site and someone's like, click here now, President Trump or President Biden needs to know if you have his support or he has your support. That's a classic example of a self-selected sample. It doesn't say nothing at all, but it's really biased by who ends up in it. So what these both have in common is they're both biased. In other words, they don't actually represent the population. So I want to show you a really beautiful idea here. And we're going to come back to a slide like this a million times in this class. This is the most important graph in this class. Don't worry though, I know we have a quiz coming up. We've got a bunch of other stuff. I'll show it 50 more times. But why is it that we like random samples? And I think we should probably end on this note because it's kind of a high note. So when you have a true random sample, so it's not biased, it's just as random as possible. Randomness is hard to define, but just think there's nothing that predicts who would end up in this sample. It's just a subset of the population that I could have gotten any, one of a million ways, right? So what's so great about that? Well, what it does is it tells us that we have a sample that doesn't have a bias in any particular direction. So that sample is going to be different to the population in some way. But let's say we're concerned with, say, the mean wage in the United States. And let's say we want to take this sample and figure out what's the mean wage. We know that the random sample will probably be wrong, but it's not going to be biased. So it won't be predictably larger or predictably smaller. When we get that sample, we know it's probably a little bit smaller or a little bit bigger, but we're not sure how. And it's actually a really good thing. And what that means is that if we really do have this random sample, it turns out that that sample comes from a distribution that's a meta kind of distribution. It's a theoretical distribution called the sampling distribution. And we'll talk about this for the whole second half of the course. The sampling distribution is the distribution of some sample statistic across all possible samples. Yeah, question.
What about like samples that are like something like from the US Census records?
Yeah.
Or like these
Sure.
are factual, these aren't just like random.
So census records, generally speaking, wouldn't be samples. They technically still are because not everyone's included, but we actually can't use a bunch of the math that we use because they're not the entire population. They're probably 95%. And it's a biased 95% because who gets left out of the census? It's usually people that are homeless, people that are struggling with addiction and so on. So yeah, census math is actually really hard. Great question. So let's say we have a really small sample that we truly do think is random. If we could retake that sample a million times, it turns out that even if the underlying variable is skewed, so like, let's say this is wages for people in the US from the CPS, notice that the distribution is really skewed. If we took the sample mean from that group, and then we redid that survey a million times, it's a mathematical fact. It's not just a convenience, and it's not just a thing that happened one time. It's a mathematical fact that that distribution of means is normal. That's known as the central limit theorem, and it's a really, really beautiful idea, but it only works if we have samples that are random, and it works because the samples are random. So you can kind of think about it like this. The farther you get away from the true mean here, the less likely you are to be observed. Or in other words, the sample mean is less and less likely the farther and farther it is from reality, because it depends on having a really freak coincidence. So if the mean only differs from the sample mean only differs from the true mean by freak coincidence, you're more likely to be close to the true mean and less likely to be far away from it. And it turns out that the exact proportions are the normal distribution. That's the whole point of the second half of the course, and it's a really exciting idea. Galton, that person we were talking about a few weeks ago, said that if the Greeks knew about this idea, they would have deified it and had a cult about it because it's such a cool thing. So let's end there. Good luck on the quiz. Happy to see you in office hours now or answer questions. I don't think it's too much to worry about. So I hope you all have a great weekend and week. Thanks, everyone.